Hey guys, what's the crack? Hi Amina, hi Gabriel. My dog's currently going crazy. I'm just waiting for it to load. Savanik, hi. What's up? What do you mean hi? How do you do? I'm grand. How are you guys? Can you see and hear me okay? Just give me like a heads up. It was a yes, please. Like a plus in the chat if we're good. Yeah, I think we're good, right? Yeah, thanks, Garrett. Savanik, how are you doing? I haven't even started school yet because I think my old school, I think they all started back today, the kids. Suppose you guys wouldn't start school. I'm talking crap, but because it's 11 a.m., so it'd be a bit weird. Unless you got free periods, I guess. Area, you got a six in physics. Happy days. So that means you're doing physics next year, yeah? Well, hopefully it means because you're doing a summer school, right? Starting Tuesday. Flip, summer went so fast, didn't it? Mad fast. Wait, Area, what do you mean no, sorry? You're not doing physics next year. Wait, so how come you're with us in summer school? I think it's great. I love that you are, but how come? Stefanik, I'm back. Where'd you go? Oh, Area, did you not? What did you need in your school? Because most schools accept a six. Quantum computing. Yeah, that's where money's at, right? Because it's a lot of coding. So if you're trying to get ahead, because a lot of times in uni, just a heads up, they assume that you already know how to code. So it's not like a lot of courses. So, for example, when I did astrophysics, they assumed that we knew how to code. We didn't have classes teaching us how to code. And that's quite hard as a first year uni trying to figure out how to use Python and C++. But there's like loads of apps on the App Store where you can see like they teach you how to code, like how to print your name and etc. as a beginner. You need a seven physics, but you got six. Area, like if you love it, like I don't know what your school's like, but I do know for my school, last year we let in a student who had a six. So you just have to like really kind of annoy them a little bit, I guess. So how we did it in my last school was if there were students like you who really love physics, but maybe they didn't get the grade, we let them do the course for let them do the course for a month, and then we do a test after that month. And if you did well on the test, it seems everybody else in the class, then you deserve to be there, right? But then if you didn't do well on the test, then that was when you had to drop it. So I don't know what you're choosing to do, Area. Like it's completely up to you. But if you do love physics, right, like you can choose four subjects and then after a month drop one. So yeah, just what I see now, you're doing biochemistry and psychology, right? So you could ask, could you try physics? Or well, more likely your mom or your carer, right? Because let's be real, like adults get listened to more than children, right? You're not a massive physics person. You must be. You're in summer school with me, like mucky pinkle pants. I jumped scared you. What do you mean? Like my voice is too loud today? Oh, you are doing coding, Savnik. Good on you. Like you do it in school, coding, like a class. The App Store. Do you use Mac? No, it's the iPhone. I thought it's called the App Store, is it not? Gabriel, biochemistry and psychology. Gabriel, why not do physics? Why not try it? Do it for like a month. And then if you get the same grades as everybody else, then you're happy. You're flying, right? Oh, Area just came on to tell me your grades. Oh, you're leaving now. Oh, well, thank you so much for being part of summer school. And well done getting a six, because six is amazing. Like, you were playing something right. Physics is the only issue in the MedCat test in Pakistan. Ishan, are you from Pakistan? Are you in Pakistan right now? Oh, it's 11:04, isn't it? So we'll get started. Today we're doing antiparticles and quarks. So it's a topic you do at the end of year 12. Well, that's when I teach it in year 12, but I guess some schools, depends on your teacher, when they like to teach it, right? It's probably my favorite topic. I really like this topic. So that's what we're doing today. Okay, so first thing there is looking at Einstein's equation. So E equals mc squared. And can you look at my data sheet? So I've given you like a snip of the data sheet there. Can you figure out what the energy of a proton is? So look at the energy of a proton. So look at the data sheet, figure out what mass you're using, and then see the speed of light squared. Give me the energy of a proton. And then we're going to talk about what an electron volt is after. Ishan, that's well cool. So you're there, are you there right now, do you mean? Or do you mean like you just are Pakistani and you're living in the UK? Kind of cool if you're living there right now. What's that? Yeah, so this is just all I want you to try. So I want to figure out, so E equals to mc squared is like Einstein's famous equation. So E stands for energy. So we're saying that the energy is equivalent to the mass. So energy and mass are interchangeable. So energy is equal to mass, and C is your speed of light. So we always use C to represent the speed of light. So, but the speed of light, C, is squared. So I want you to figure out, look at a proton. Okay, so a proton, remember, is that thing inside the nucleus. Yeah, Gabriel. Yeah, brilliant. So a proton's thing inside a nucleus. So I've given you the speed of light here, but hopefully you all know that number, 3 times 10 to the power of 8. So 3 times 10 to the power of 8 is our speed of light, and that's the number that we're squaring. We've got to find what the mass of a proton is. So if we look down for you here, you can see that we find the mass of a proton is down here, proton rest mass. So the mass of a proton is this number. So you're going to use 1.673 times 10 to the minus 27. And you get your energy then in a certain unit. So pop in the chat as soon as you pop that in your calculator. What would be the energy then of that single proton? So what we're saying is a proton, even if it's not moving, right? So here's a proton here. Even if it's not moving, because it has mass, it has some energy. And we're trying to figure out what energy that proton has because of its mass. So in your calculators again, you're typing 1.673 times 10 to the negative 27 multiplied by 3 times 10 to the power of 8, all squared. Quite nice because I think like you see this equation, Einstein's equation, like everywhere all through school, right? But they never really get to use it. So like this is the first time you've probably used it, right? Monkey pick a pants, 1.503 times 10 to the power of negative 10 is perfect. Yeah, good job. So it seems what I got. So 1.5 times 10 to the negative 10 joules. Okay, so just give us a little yes if we're good, if everyone else is happy with that number. 1.5 to the negative 10 joules. Yeah, perfect. Yeah, fab. Perfect. Perfect. So now the next thing we're going to do is we're going to talk about, do you see how that's right, an annoying number to write because it's such a small number? So again, the mass of proton, because the mass of proton is so low, the energy is so low. So it's an annoying number. So what they've decided is what we use in particle physics is we use a thing called an electron volt. Okay, so E stands for electron, and then the V stands for volt. Okay, so electron volt. So the way I kind of figure it out is it kind of similar to chemistry. So you've all done chemistry, moles, right? So remember you talk about moles, 1 mole or Avogadro's constant, I think it's here too, is 6.02 times 10 to the power 23 particles, right? So that means because there's so many particles, we're going to write it in moles instead to make our reference easier. So again, because these energies are so low, we're going to write them in electron volts instead. So what an electron volt is from GCSEs, you've probably done E equals VQ. So energy is voltage times charge. So what an electron volt is what the energy is when we accelerate the charge of a single electron through a potential difference of 1 volt. So again, the potential difference is 1 volt. The charge is that of an electron. So if I look here, the charge of an electron is different now. So you know how you in school, you always said the charge of an electron is -1. That's a relative charge, okay? It doesn't actually have a charge of -1. Its charge is this number, 1.6 times 10 to the negative 19 coulombs. So you multiply those numbers together, obviously you get 1.6 times 10 to the negative 19 joules. So what we're saying is 1 electron volt now is equal to 1.6 times 10 to the negative 19 joules. Yeah, I mean, I will do it again. So just to have a look here though. So if I have 1.5 times 10 to the negative 10 joules, and I want to put it into electron volts, you can clearly see we just divide by 1.6 times 10 to the negative 19. Okay, and when you do that, when you divide by 1.6 times 10 to the negative 19, you get 941 times 10 to the power 6 electron volts. We can write that as 941. What's that? I said 6 and wrote 10. 941 mega electron volts. Okay, so I'll talk for that again because that's probably something that's very new. So I'll highlight it. Okay, so again, in GCSEs, right, we all said that the mass of a proton was +1. Okay, but mass of a proton is 1. Okay, but the mass of proton is not actually 1, right? It's not actually a mass of 1 kilogram. That wouldn't make any sense because the proton's tiny, right? So the mass of the proton is what you see here. So I look down here, my mass of my proton is actually 1.673 times 10 to the negative 27. That's why up here, when we did our equation, the energy, the mass of that proton, we don't use 1 because the mass of proton is not actually 1 kilogram. It was a relative mass. So its mass is 1.673 times 10 to the negative 27. Same thing we talk about charges. So charges of electron in GCSE, we said charge is -1, but again, it's a relative charge. So in your data sheet, you can see the charge of an electron is actually 1.6 times 10 to the negative 19 coulombs. It's my charge of my electron. Okay, so what we're saying here is we just calculated how much energy that proton has, okay? But that energy, because it's so small, we want to always write it now in a thing called electron volts. No, Aaron, you get this data sheet. So in your data sheet in your year 12, this will be the very front page. So every time you do a question, you'll just have that sitting beside you. So you always just look at these numbers. So you always have these numbers. But I can guarantee, Aaron, after 2 years of doing physics nearly every day, you'll have memorized most of those numbers. I kid you not. I know it might seem a bit shocking now. You're like, no way I'll remember those. But you probably will without meaning to by the end of the year. But you always have it open beside you just in case, right? So 1 electron volt, what it is, so this just means describing to you what it is. It's the E equals VQ. An electron volt is the energy when we accelerate a single electron for a potential difference of 1 volt. So an electron has a charge of 1.6 times 10 to the negative 19. We're accelerating it for a single volt. So that's why its energy is 1.6 times 10 to the negative 19 joules. So all you need to know from that is every time that I want to write my energy for particle physics, only we're talking about particle physics, instead of writing your energies in joules, you'll always write it in electron volts. So to get from joules into electron volts, all you have to do all the time is divide by 1.6 times 10 to the negative 19. So that's what I've done there. So I have my answer in joules, and to put it into electron volts, we divide by 1.6 times 10 to the negative 19. Okay. Okay, how do we feel about that? Because that's like a lot of learning straight into it, right? Because again, in GCSE, you've probably just said charge of electron is -1, but right, doesn't make sense it's -1. It's a relative charge. Or for example, the charge of a proton is +1, but that's a relative charge. It's not actually +1. It's going to be the opposite of the electron, so it's going to be positive 1.6 times 10 to the negative 19. Okay. Okay, just because that was a lot long ago, I think we'll just practice that again. Okay, so we're just going to move on here to first, I want to talk about what particles and antiparticles are. Actually, I'm just going to go back there, sorry. So here you can see a photon, you've probably never seen that word either. A photon is what we call a beam of light. Okay, so we know that light is a wave, but we can also say it's made of things called photons. Okay, so you learn about that when you do waves in physics. So we say that beam of light is made of photons. That makes sense, right? Photo, if you take a photograph, it's to do with light, so photons. And if I have a beam of light, that energy, all that energy from that light, because energy and mass are interchangeable, that beam of light can make me a proton and an antiproton. Yeah, relative charge. Yeah, so I'll put my pen up. Okay, so let's go in blue. Oops, it's not a pen. Give me a hot sec. Pen. Blue. Okay, so do you know in GCSEs when you had that little table? And the little table said what is the mass and what is the charge of the different components. So you had a proton, you had a neutron, electron. So everyone said the mass of a proton was 1, the mass of a neutron was 1, mass of electron was basically 0. The charge of a proton we said was +1. The charge of a neutron we said was 0. The charge of an electron we said was -1, right? Those were the relative charges and masses. So that means is if the charge of an electron is actually 1.6 times 10 to the negative 19, when you divide that by that same number, 1.6 times 10 to the negative 19, you get 1, right? So again, if the charge of an electron is actually negative 1.6 times 10 to the negative 19, when you divide it by 1.6 times 10 to the negative 19, you get -1. So that's why we put -1 on the table. It's a relative charge. Or the mass of a proton is actually 1.6 times 10 to the negative 19. So we divide through by that same number, 1.6 times 10 to the negative 19. That's why we got +1 for the charge of the proton. Okay, same for the masses. So again, if you look at the mass of a proton down here, 1.673 times 10 to the negative 27, we said its mass is 1, but it's not actually 1. It's actually this number. Just divide it through. The mass of a neutron, hopefully you can see if it's 1. The mass of a neutron is the same thing, 1.67 times 10 to the negative 27 kilograms, right? It's just because in GCSE physics, you wouldn't use those large numbers, or wouldn't use those really tiny numbers. So that's why we learned it in relative terms to make it easier. Happy? Okay, so what we're saying here now is what we're doing for particle physics is we're saying that we're going to use these numbers from now on. We don't use +1 and -1. We use these numbers from now on. And what we're talking about now is we know there's things called protons. We have protons all the time, all for Key Stage 3 and GCSE. But now we have a thing called an antiproton. So an antiproton is antimatter. Does anyone know about antimatter before I go into teaching it? What is antimatter? So matter is like what our universe is made of, right? Like my body's made of matter, you're made of matter, I'm made of real protons, real electrons, real neutrons. That's what my atoms are made of. But there's also a thing called antimatter. Do you know what it is, or where did it go? Antimatter. No, not heard of it. Negative mass. It's actually got the same mass. It's something else that's opposite. So antimatter, right? So antimatter, I think this is fascinating. So it's a big topic in physics, and it's actually quite a big research topic right now. I can't even spell research. It's quite a big research topic right now because we're not exactly sure where it all went. Okay, so we know the Big Bang is the current theory, right? It's not a fact yet because we haven't really figured it out completely. So it's a theory. But the Big Bang is a theory where we think that the universe was created, right? It's the best option right now. So we think that's how all matter was created. And we got equal numbers of particles and antiparticles made, right? So everything was created in the Big Bang, particles and antiparticles. But our whole universe is made of particles, right? Our whole universe is real matter, real particles. So the big question in physics right now is where did all those antiparticles go? Okay, so like if there were equal amounts of them at the start, where'd they all go? And one of the biggest theories is that let's say I've got a proton and I've got an antiproton. So the way we show an antiproton is you just put a little line over the top of it. Okay, so for example, if that's my neutron, my antineutron is we just put a little line over it. So what happens is anytime you have real matter and it meets antimatter, when they collide with each other, we say they annihilate. So what that means is like they destroy each other. And when they annihilate each other, there's going to be loads of energy that comes out. So we're going to get loads of energy that comes out. So again, what we're saying is anytime matter meets antimatter, because they collide and they annihilate each other, they destroy each other, we get energy created, right? But then that would mean we shouldn't have any particles or any antiparticles in our universe, right? But we do. Our whole universe is made of particles. So again, the big question is why is there more real matter in our universe and there's no antimatter? So some of the theories right now is they think that antimatter decays slightly quicker. So it basically left the universe much quicker than our real matter. But again, it's a massive question. It's a massive part of research. So again, it's quite cool to learn about physics because again, you're learning like the top of the level we know, right? So we know there is antimatter and we know that because of CERN. So CERN, there's like really large hadron colliders. And what they do is they take particles and they basically just fire them at each other. So we get particles and we fire them at each other at really, really high speeds. And then we see what the energy comes off. And when they look at how much energy comes off, because we know E equals mc squared, if we know how much energy these particles have, we can figure out how much mass the particles have. So what we figured out was that matter and antimatter, they have the exact same mass, they just have opposite charges, right? So if I told you I've got a proton and its relative charge is +1, what's going to be the charge in the chat of an antiproton? Same mass, opposite charge. So if I told you I've got a real proton, its charge, relative charge is +1 or plus 1.6 times 10 to the negative 19. If I have an antiproton, yeah, Gabriel, beautiful. I mean, beautiful. An antiproton, it's going to have a charge of -1 or minus 1.6 times 10 to the negative 19. Okay, what about an electron? An electron, we learned from GCSEs, has a relative charge of -1 or negative 1.6 times 10 to the negative 19. If I have an anti-electron, what charge or what relative charge is it going to have? An anti-electron. Yeah, I mean, easy, right? +1, because it's going to have the same mass, just opposite charge, or plus 1.6 times 10 to the negative 19. Did any of you know what do you call an anti-electron? So it's got a name, actually. So an anti-electron has its own name. Begins with P. Kind of sounds like its charge. So an electron is -1, and an anti-electron is +1. Its name is, does anyone know? Yeah, user 96, good on you. Yeah, it's called a positron. So it's called a positron. So an anti-electron is called a positron. Yeah, so that's what you can say now. It makes sense because it's got a positive charge, like positron, positive. Okay, so we're going to practice all that again. So really quickly, because we just said it, can you pop in the chat, what do you call the antiparticle of the electron? User 96 probably is like, I just typed it, but, or you can look at user 96 answer. So what is the antiparticle of an electron? Yeah, Amina, nice. So that's just, we're trying to get used to the vocab now, right? So there's probably quite a lot of vocab in physics, but it's a really nice topic. Yeah, positron, 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 nice. So an anti-electron is also called a positron. Okay, positron. Okay, what is the similarities and the differences between particles and their antiparticles? So what's the same about particles and their antiparticles, and what is different about particles and their antiparticles? From the chat. What's the same about particles and their antiparticles, and what is different about particles and antiparticles? What's the same and what's different? Same mass, Amina, same mass, Gabriel. Gabriel, different charges. Yeah, perfect. Easy, good job. Yeah, different charges, Amina, nice. So particles and antiparticles, they're going to have the exact same mass. So the same mass, but the only difference is they're going to have opposite charges. Right, so example, earlier we said an electron, if I look at my electron down here, and my electron has a mass of 9.11 times 10 to the minus 31. So it's got a mass of 9.11 times 10 to the minus 31. And its charge, if we look down here, the charge of my electron is 1.6 times 10 to the negative 19. So it's got a charge of minus 1.6 times 10 to the negative 19. But the positron is going to have the same mass, 9.11 times 10 to the minus 31, but opposite charge, so positive 1.6 times 10 to the negative 19. So exact same mass, just opposite charge. Okay, what does this equation mean? E equals mc squared. Just pop in the chat. What do the terms represent? E equals mc squared. You've probably seen this all your time through school, right? Like it's everywhere. It's not like every physics classroom probably has up in the room somewhere on a board, right? E equals mc squared. What does it mean? So we just talked about it in the first slide. It's Einstein's equation. E is energy, m is mass, and c is the speed of light. Thank you, Bill. Good job. So E is our energy, m is our mass, and m naught, just put it down for you, m naught is me telling it's the rest mass. Okay, so if you look at our data sheet here, do you see it says proton rest mass? So what the rest mass means is if I have a proton and it has 0 kinetic energy. So remember, kinetic energy is things are moving. So if it's 0 kinetic energy, it's not moving. So the rest mass says if my proton's just stuck in space, it's not moving, I can figure out how much energy it has by doing its rest mass times the speed of light squared. Hi, Angel, you all right? You kind of missed a little bit, but hopefully this slide's just us all going over it again. E is energy, m is mass, and c is speed of light. Good job. And the speed of light, we all know, is 3 times 10 to the power of 8 meters per second. Nice. Okay, what if I asked you to draw a diagram to show the pair production of a proton and antiproton from a single light wave? So what we're saying is I've got a single ray of light coming in, I'm going to make a proton and an antiproton. How would I show what directions they go in? So for example, I'll give you options. So there's going to be my proton and my antiproton. So that's option 1. Option 2 is going to be proton and antiproton. And option 3 is my ray of light, proton and antiproton. So which one's right? 1, 2, or 3? Yeah, Gabriel 3. Do you know why? Can anyone tell me? So Gabriel says 3. 100% agree with him, her, sorry. Don't know. And Amina says 3. Why is it 3? So for example, maybe it's easier to say why it's not 1 and not 2. Right, think about number 2. It can't be number 2 because if they're both going in the same direction, they're probably going to hit each other and they're just going to annihilate each other. They just get destroyed again, right? So that doesn't make any sense. Number 1 is if we think about vectors, right? If number 1, before I've got a vector going towards the right, and after I've got a vector going up and a vector going down. So I didn't conserve my vectors there, right? So before, if the vector is going towards the right, after the vector also has to be going to the right. So it can't be 1. Whereas in 3, I've got a vector going to the right before, and after I've got a vector going up and a vector going down. Remember we did resolving vectors? So this vector, what it really means is I've got an upward component and a component going to the right. And this vector, what it really means, I've got a downward component and a component going to the right. And hopefully you can see my ups and my downs would cancel. So that's why I just have my 2 vectors going towards the right. So overall, I'll have a larger vector going towards the right. So it's being conserved. So what we're just saying is we're conserving our momentum, okay? Yeah, so the overall, when we resolve the vectors, we're going to have a vector that's going towards the right because the upwards and downwards components of those vectors cancel, okay? So the reason it goes this way, the reason it goes this direction is because we're saying that our momentum is conserved. Okay, so our momentum is conserved. Ishan, what? Where did you come from for 1? We just talked through it can't be 1, right? Because remember, the before was a vector going towards the right, and the after was a vector going up and a vector going down. So those 2 vectors would cancel, leaving us nothing after. So where did our vector go that was going to the right? Okay, so that's why it couldn't have been that one, because we weren't conserving our vectors. Remember we did the lessons on vectors, right, where we resolved our vectors. Okay, can anyone figure out what the energy now is of that photon? So here's my energy or my photon going in. I want to know how much energy goes in to make my proton and my antiproton. Remember, we're using something to do with this equation. So see if you can figure it out and pop in the chat. What is the energy of that photon? And question C, where I did, because we just said we want to conserve momentum or conserve our factors. So I'm asking here, what is the energy of the photon? What's the energy of light that we need in order to create pair production? So it's pair production because they're created in pairs. It's matter and it's antimatter, the pair. So hopefully you're thinking, I need to figure out how much energy that proton has. And hopefully you're thinking, I need to figure out how much energy that antiproton has. And then figure out how much energy that ray of light had to have to go in. So hopefully what we're doing here now is we're doing E equals mc squared. So energy is the mass of a proton, which we said was 1.673 times 10 to the negative 27, multiplied by the speed of light, 3 times 10 to the power of 8, all squared. Then I've got my energy of my antiproton. I know antimatter has the exact same mass, so it's still 1.673 times 10 to the minus 27, multiplied by 3 times 10 to the power of 8, all squared. So if this is our energy after, the energy before must have been the same. Because remember, we learned in physics a long time ago, the energy has to be conserved, right? Energy can't be created or destroyed, only transferred. So what I need to do when I find these 2 energies, I just need to add them together to figure out what my final energy there is of that ray of light going in. So hopefully everyone got 3.02 times 10 to the negative 10 joules. So let me know if you're good with that one. So again, we got a proton created, so that's why I do E equals mc squared. And we have an antiproton created, so I do E equals mc squared. But because we have two energies after, the energy before has to be the same. Energy can't be created or destroyed, only transferred. So we add the two energies together to figure out what energy of light, what energy that photon had to go in to create those pair production. Okay, Amina, thank you. What about everybody else? How are we doing? Yeah, we're good. We're good. Happy days. Okay, so number 4 we're on now. What if I told you we're doing annihilation? So I've got annihilation. So I've got an electron, which is my negative charge particle. It's going in and it's going to collide with my positron, my positive charge particle. So I'm going to give you options again. Is it going to be option A, option B, or option C? What would be a correct diagram? Okay, so again, electron coming in, positron coming in, electron coming in, and we know they're going to annihilate, positron coming in. Okay, so option A, is it going to be one ray of light with energy E? Option B, are we going to get a ray of light, a photon going up and a photon going down? And option C is, are we going to have energy going like this? Which one makes the most sense? So A, B, or C. What would be a diagram to show us annihilation, a particle and an antiparticle, matter and antiparticle colliding with each other to conserve the momentum? So Amina says A. What do we think? Do we agree with her, disagree? Or him or her, sorry. So remember, think about our vectors. So remember before, if we look at this side, her. If we before we look at this side, we had one vector going in, and then after we had a vector going up and a vector down. So we said we can resolve those in up to the right, down to the right. So my up and down cancels. So that's how I just get left on my right after as well. So here in section A, I have a vector going towards the right and a vector going towards the left. So hope you're thinking those are opposites. And now I've got a vector going up. So it can't be A. Because what we had before, remember, was a vector going to the right and a vector going to the left. Those two would cancel each other. But after I've got a vector going up, so it doesn't make any sense. I haven't conserved anything. I've created a vector going up. Okay, C. So C, I've got a vector going towards the right and a vector going to the left. That's before. So technically they would cancel each other. After I have a vector, so this energy can be resolved into down and to the left. And this vector can be resolved in down and to the right. So hopefully you're saying, yeah, the right and left will cancel, but I'm still left up with a vector after going down that I didn't have before. So it can't be that one either. So in fact, it had to be option B. So have a look at option B to see if we go with that. Before, a vector going to the right and a vector going to the left. So they're going to cancel each other. And then after, I've got a vector going up and a vector going down, and they're also going to cancel each other. So this is the only one where I've conserved my vectors. So again, before, we have a right and we have a left. Those technically cancelled to have nothing. After, I've got up and a down, but technically those cancelled to give me nothing. So that's why the momentum is conserved in that diagram there. Okay, so now we know what the diagram looks like. Can you figure out what the wavelength is of the photon? So step 1 is you need to figure out what the energy of the photon is. And then once you know what the energy of the photon is, look over here. I've told you energy of photon is hc over lambda. Okay, so again, it's a lot of new learning. So once you find the energy, you're going to say that energy is equal to h times c over lambda. H is Planck's constant. So I'll give you the number there. So H is called Planck's. Oops, can't see because of my head, sorry. H is called Planck's constant. And then C, we know already, is just our speed of light. So give it a go. Be brave. See me the first. I'll change my colors so we can see we're in a different question. Be brave and pop in the chat when you think you have it. And hopefully you're quite enjoying learning all this new stuff, right? Like this is like, I don't know about you, but I feel like physics in GCSE is just F equals ma, kinetic energy is half mv squared. It's quite basic stuff. But when you do physics for A level, it's quite nice. You're using Einstein's equations. You're using proper data sheets of the proper figures. E equals hc over lambda. And you get given that equation, so you don't need to learn it. But again, because you'll use it so much, you'll have learned it without meaning to. So I'm trying to figure out the wavelength of the photon. So I said the first thing I got to figure out is what energy this photon has. We know energy is conserved. So first thing is figure out what is the energy of that electron, what's the energy of that positron, and then I've got two energies going in and two energies going out. So both of these waves photons are going to have energy. I just want to know what energy of one of them is. So hopefully you're thinking E equals mc squared. So the energy of that electron is the mass of my electron. The mass of my electron is written here. So the mass of my electron is 9.11 times 10 to the minus 31. And I have to multiply that by the speed of light, 3 times 10 to the power of 8, all squared. And then I can see now I've got a positron here, and we know antimatter has the exact same mass, just opposite charge. So it's still 9.11 times 10 to the minus 31. And we have to multiply by 3 times 10 to the power of 8, all squared. And hope you're thinking the energy before is going to be both of those added together, right? Because remember, energy is scalar. It doesn't matter about the directions. So the energy before is going to be both of them added together. But then if I look at it, I've got 2 photons produced. So the energy after is actually going to be half of that again. So the energy after is actually just going to be equal to one of those. So what I got the energy after to be is 8.199 times 10 to the minus 14 joules. So now you have the energy. Can you figure out what the wavelength is of that photon? So let me know if we're good with the 8.199 times 10 to the minus 14. Yes, happy. Gabriel, thank you. What about Angel? How are we doing? Did we catch up okay? Ishan, how are we doing? Monkey Picker Pants, I've lost you. Savanic, I've lost you as well. So how are we doing? Yeah, you're good. Have days. Did anyone get the wavelength then? Savanic, Monkey Picker Pants, how are we doing? Gabriel, wait. Yep, what's up? Tell me. So we're trying to find the wavelength now. So to find the wavelength, I know the energy is equal to hc over lambda. So all I have to do to find the wavelength, I do Planck's constant, 6.63 times 10 to the negative 34, multiply by the speed of light, 3 times 10 to the power of 8, and I divide that by the energy, which is 8.199 times 10 to the negative 14. So when I did it, I got a wavelength of 2.43 times 10 to the negative 12 meters. So give me like a yes if we're happy and no if we're not happy. Manish, a block A, 2 kilograms kept in a block B, 4 kilograms, and block B, the coefficient for each within block B. Wait, Manish, are you just like popping in some questions for me here? Gabriel, you got the same number? Yes. How is everybody else feeling? Feeling happy? Not feeling happy? Okay, so we'll try another question then. Okay, so same math. We're just doing it with different particles now. Okay, so what I've told you here is a muon is like a heavy electron. Okay, so a muon is another particle we've not heard about, but all it is a heavy electron. You can see it's got a charge of -1. So an electron, remember, it's got a charge of -1. A muon is just a heavy version of it. So draw me a pair production of a muon. So pair production of muon, hopefully you're thinking energy of light goes in. Pair production means I'm creating two things. I'm going to create my muon, which it told me it's got a negative charge, and my antimuon, so I know same mass, opposite charge, it's going to be a positive. So there's my pair production of my muon. I've got my real particle, the muon, and my antiparticle. So I've told you now what the mass is. So the mass of muon is this number. What is the frequency of the photon to create that? So the first thing you got to do is figure out what is the energy of that photon to create it. And we know the energy, the equation is equals HF, or energy equals hc over lambda. And the number you're going to use for h is Planck's constant, 6.63 times 10 to the negative 34. So if I want to find the frequency, first thing I ought to do is find the energy. Then I got to divide that by Planck's constant to find its frequency. And I know the energy of that ray of light, energy before, must equal the energy after. And we know the energy after is going to be equal mc squared of our muon negative, and we have to add it to the energy mc squared of our muon positive. And we know that antiparticles have the same mass, they just have opposite charges. And I told you the mass up here. So give it a go and then pop your number in the chat, either for the energy or for the frequency. So either for the energy or for the frequency. Manish, I'm a JEE aspirant. JEE Advanced is the second toughest exam in the world. I'm not going to lie to you, Manish. I don't know if I should know this, but what's JEE? IIT. I'm sorry, but it's another acronym and I still don't know what that is. Second toughest exam in the world. What's the first toughest? The Indian Institute of Technology. Ah, okay. And then to get in, you have to take the JEE. How do you know it's the second toughest exam in the world? Who decides this? Do you know? Gabriel, is yap mean you've got the answer? How do you know it's right yet? Give me the answer. I'm gonna write these down, Manish, because I've never heard of them, so I can look them up after. What'd you say it's called? The JEE. I guess there's past papers you can download so you can see them, isn't there? GAOKAO. Okay, so for this one, hopefully what we're doing right now is you figured out what the energy of the muon is. So E equals the mass, 1.88 times 10 to the negative 28, multiplied by the speed of light, 3 times 10 to the power of 8, all squared. So when you figure out that energy, when I did it, I got 1.692 times 10 to minus 11. You got 1.128 times 10 to the power 21. Just check that. So mass times speed of light squared. And then that's the energy of just one of them, but I have two of them. So I'm going to multiply that number by 2 to get a final energy there of 3.384 times 10 to minus 11 joules. And then for the last bit there, we're doing E equals HF. So in order for me to find the frequency, I just have to take my energy, 3.384 times 10 to the minus 11, and divide it by Planck's constant, which is 6.63 times 10 to the negative 34. And I got a frequency of 5.1 times 10 to the power 22 hertz. I mean, you didn't square. Yeah, E equals mc squared. Yep. Yeah, and it's good you're noticing this stuff now, right? Because there are like things that people do all the time in their tests. And the USMLE in the United States is 3 of the tough exams in the world. What are they, Garrick? Are they physics exams or are they science exams? Or are they like science and English and math? 3.384 times 10 to the minus 11, Amina. Yeah, beautiful. And then, hi, Chatterjee. And then when you converted it into frequency, did you get 5.1 times 10 to the power 22? Chatterjee for year 12? Yes, it is. Where have you been for the last, what are we at? We've only got 15 minutes left here. I thought you were coming to all the year 12 lessons. But today is like intense A-level physics. So you wouldn't do any of this in your GCSEs. Oh, you're doing math? I guess I can excuse that. Okay, so how do we feel about the frequency of our photon or energy going in? Monkey Picket Pants, you're back with us. Are you happy with the numbers for frequency? Manish, it's physics, chemistry, and math. Oh, okay. And that's probably why it's really hard then, right? Because those are free of the like intense subjects. Muggy Pick, you're confused. Where'd you go for half an hour there? You tapped out on us. Gabriel, you're good. Happy days. So just to give you a recap there, Monkey Pick Pants, what we said was the energy, we used the equation E equals mc squared. So we took the mass of our muon, which I told us what it was, times speed of light squared to figure out what the energy of that muon was. But because we've got a muon and an anti-muon, that's why we had to multiply by 2 to figure out what the total energy is after. And the total energy after must be equal to the total energy before. So now we know the total energy before is the same thing. And their new equation is E equals hf. So to find the frequency, we just have to divide it by h. And it tells us up here that h is Planck's constant. Manage, they're easy. If they're easy, help us out and put the answers in for us. Okay, so next one is, so before we were talking about how the only energy the particles had was because of their mass equals mc squared. But now the particles are going to have energy due to their mass and they've got some kinetic energy. So can you figure out now if I've got a proton moving to the right with that kinetic energy and I've got an antiproton moving to the left with that kinetic energy, what's that diagram? So hopefully we're thinking what we're doing here is annihilation. I've got a proton coming in, I've got an antiproton coming in, and they're going to annihilate each other to create my two energies of light. I've told you one proton has got 7.2 kilo electron volts of energy, and the other proton has 9.0 mega electron volts of energy. So the first thing you put in the chat, what is that 7.2 kilo electron volts in joules? So pop in the chat. And then the second thing to pop in the chat is what is that 9.0 mega electron volts in joules? Okay, because I give it to you in electron volts. Okay, so in the chat, what is the energy in joules of the photon? What's that kinetic energy in joules? And what's the kinetic energy of the antiproton in joules? Chatterjee, did you say your first name? Is it Suryanshu? Is that how you pronounce your first name? Suryanshu. But we've got GCSE physics on Friday. So you see me Friday. Ah, I said it right. So yeah, Friday. Right, in the chat, what we're thinking, what's the energy of that proton? What's the energy of that antiproton? So hopefully we're thinking 7.2K means 7.2 times 10 to the power of 3 electron volts. Hungry Piggy Pants need to rewatch. To be fair, these, I really love this topic, right? But it is a lot of new stuff. I like the topic because it feels like proper physics, right? It feels like you're looking at muons, looking at new particles. You've probably never heard of a muon before, but it doesn't matter. It was just seeing if you understood that when you do pair production, both the particle and the antimatter is created. 1.152 times 10 to the negative 18. Negative 18. Ah, Gabriel, you forgot about the kilo there, didn't you? So I'm just going to rub out. So Monkey Pick a Pants, stay with us for the green one now, and then pop in the chat when I lose you, so then I can know where we're struggling with, okay? So stay with us for the green answer now. So what we're doing right now is we're trying to figure out what's the energy of that proton in joules. And Gabriel, you're basically perfect apart from you're too small. So did you forget about the kilo? So again, if I do 7.2 kilo electron volts, that's 7.2 times 10 to the power of 3 electron volts. And remember we said earlier, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So get from electron volts into joules, all you have to do is multiply by 1.6 times 10 to the negative 19, and you get the number 1.152 times 10 to the negative 15 joules. Yeah, Gabriel, perfect. Nice. Okay, so that was the energy of our proton going in. Okay, so now can we figure out what's the energy of our antiproton going in? So remember, we said its energy is 9 mega electron volts. What is that energy in joules? So what's the kinetic energy of that antiproton in joules? So hopefully you're thinking, what does 9 mega mean? So 9 mega is 9 times 10 to the power 6 electron volts. But I want that number in joules. Monkey pickle pants. Is the def because are we okay with electron volts to joules? Is that part good? So put it into joules. Sorry, Anshu, you're going to see me on Friday. You'll be grand. Okay, so you're good with the joules part. Okay, so do this part first, and then we're going to go to the next step. You're dead over what Garrick said. Yeah, to be fair, this is us getting intense now. Yes, Gabriel, thank you. Lovely. So it's going to be 1.44 times 10 to the negative 12 joules. Okay, so we just said that's how much energy they both have because they're moving, but we know there's another energy as well there. Well, we know they have energy because they have mass equals mc squared. So now to find the total energy before, we have to find the energy because it was moving, it's kinetic energy, and we have to add it to its energy because it's got mass. Okay, so can you now figure out what energy the proton has because it has mass? So remember, we look over here, the mass of a proton is 1.67 times 10 to the negative 27. So what energy does it have now because it has mass? And then the total energy is going to be, we add them together. I mean, it's crazy. Crazy good, and you're like, wow, look at what I'm doing, or crazy as in, whoa, too much. So again, now we're trying to figure out how much energy it has. So what we're thinking is I have to find the mass of my proton, which is 1.673 times 10 to the negative 27, and then multiply by the speed of light, which is 3 times 10 to the power of 8 all squared. You have to rewatch it. And I mean, that's, yeah, like this is particle physics, right? So this stuff you're going to learn, it's probably going to take you a month in school to learn, right? But summer school is just me trying to give you a little bit of stuff. So the first time your teacher talks about electron volts, you're not going to have a bit of a panic, right? So hopefully you'll be like, oh, I remember doing a little bit of summer school. The first time your teacher teaches you muons, you're going to be like, doesn't matter what it is. All I know it's a heavy version of electron. Or hopefully you'll have heard the word positron. And like you just said, like all you there, it's about rewatching it. When you go to learn it in school, at least you have this to go back to, is right. And hopefully you'll be in the September course with me. So we'll spend quite a few lessons on this. It won't be just one lesson done, right? How can you keep in touch with us after Friday? TikTok and Instagram. But sure, I've been chatting to you on TikTok anyway. Gabriel, thank you. 1.5 times 10 to the negative 10. Yeah, easy, good job. So that energy there, when you multiply those numbers, is 1.5 times 1, say, times 10 to the negative 10. And it's going to be the same on this side, E equals mc squared, because the antimatter has the same mass, just opposite charge. So 1.51 times 10 to the negative 10. So now figure out what the total energy is before of both of those things. So, because remember, when they annihilate each other, we get two photons produced, traveling opposite directions, conserve momentum. But in order to figure out what the energy of one of those photons is, I need to know what the total energy is before. So can you now figure out what the total energy is before? So remember we said the energy is because it's got energy due to its mass and energy because it's moving. So to add those together, find the total energy of the proton before. And the total energy of the antiproton before is due to because it's moving, it's kinetic energy, and its mass. So the total energy before is then we add the total energy of the proton to the total energy of our antiproton. So just pop in the chat, what's that total energy then before? Manish, me ignoring you. What I miss? Monkey Pickle Pants. Is your brother just finished? A level physics. Manish. In physics, we need to solve the equations which are solved by PhD students. To be fair, this is math that PhD students will be doing, right? Because if you're doing a PhD in nuclear physics, when you're using the CERN and looking at the data from CERN or the Large Hadron Collider, you have to use this same math to figure out the energy of the particles before and after. He just finished his master's in aerospace engineering. Oh, cool. What career does he want to do? I'm guessing, does he want to work for like ESA, the European Space Agency? What's he looking at? He got an A star in A-Level Physics. So you've basically got your own personal wee tutor there, eh? He wants to be a pilot. Wants to be a pilot or wants to do aerospace engineering in making spacecraft or like spacecraft and making airplanes. 3.0. Gabriel, yeah, thank you. So you said the total energy before is 3.03 times the negative 10. Yes, perfect. Yes, good job. So total energy before is 3. Let's say 03 times 10 to the negative 10 joules. Good job. So that's the total energy before, right? But we have 2 rays of light created. So what will be the energy of just 1 ray of light? So it's our total energy before, but I've got 2 rays of light created. So then that means the energy of 1 ray of light is going to be half of that number. So the energy of 1 ray of light is 1.52 times 10 to the negative 10 joules. So that's my energy of my photon. Okay, so now can you figure out what the wavelength is? So Gabriel, you've been on it. So remember, to find the wavelength, we use E equals hc over lambda, or E equals hf. But I don't want to find the frequency. I want to find the wavelength. So now you know the energy of my photon. What is its wavelength? Remember, I've given you Planck's constant here, and the speed of light is 3 times 10 to the power of 8. So can you figure out what the wavelength then is of that photon? Manga Picket fans, be a pilot. I think I guys told you this before. I really wanted to be a pilot up until maybe 6 years ago. Yeah, so I really want to be a pilot. So what does he want to be? A pilot in the Air Force or a pilot like commercial? I was obsessed with being a pilot. So all the best to him. Manish, you're 16. Wow, it's a different level. So Manish, what's the wavelength then? Help us out. See if tell me if your 16-year-old can get the wavelength before Gabriel. Yeah, Sirianshi, I looked it up because you were talking about being a pilot, and Garrick was right. It depends on your eyesight, and it depends what you want to do. So for commercial pilots now, they do let you fly planes if you wear glasses. So Garrick's right. It's for commercial pilots. I only knew about Air Force, so the Royal Air Force, and it depends on the level of eyesight you have. So for example, my eyesight means I can still drive a car without having to wear glasses, so I'm safe. So I can still be an Air Force pilot, but not with my age anymore. But if you need glasses to safely drive, then you can't be an Air Force pilot, but you can still be a commercial pilot. So I looked that up for you. He wants to be a commercial pilot. Oh, good on him. Yeah, so Sarianchi, hopefully I answered your question there. Oh, planes are F1. Very cool. Did I tell you about, I can't remember you guys or your 13s. I was telling about the guy that I know does F1. That's a really cool career. So he's a guy who studied physics with engineering at my school, Michigan State. And he now works for F1. So he gets flown around the world first class. So he lives in America. Imagine a first class flight from America. Like, it's lovely. First class around the world. And what he does is he just like looks at the conditions of the road, looks at how windy it is, and then he tells the mechanics like how high or low the car should be that day, how thick the tires should be, how much thread should be in the tires. He loves that job. Gabriel, 1.3 times 10 to the negative 15 is the wavelength. Yes, Gabriel, what a star. See, Manish, you were saying it's easy and Gabriel got it before you. Yeah, thank you. 1.3 times 10 to the negative 15 meters. Yeah, good on you. Because all we do is E equals Planck's constant, 6.63, times 10 to the negative 34, multiplied by speed of light, 3 times 10 to the power of 8, and then divide it by the wavelength. We know the energy, so to find the wavelength, all you had to do was 6.63 times 10 to the negative 34, multiplied by 3 times 10 to the power of 8, divide it by the energy to get the wavelength. Yeah, good on you. Yeah, that was fab. Manish, what do you mean, okay, bye? I was only joking with you. Gabriel, you're 16 as well. Ach, mate, you'd all be 16, wouldn't you? I'm confused. I keep thinking because I'm teaching you year 12, you're actually in year 12, but you're not. You've just finished your GCSEs. So you're all 16, aren't you? That's my bad. Manish, I was only joking. I was only, because you're so smart, I was only, yeah, I wasn't coming at you. Can we do a Kahoot? Sorry, Anshu, you weren't even in our lesson there for the full time. Amina, we're okay too, yes? Okay. We're this stuff, the fundamental force of nature, was stuff we were going to come on to today, but just because we spent quite a lot of time going over particles, because we spent quite a lot of time there in that first slide, understanding what an electron volt was, understanding what relative charge was and relative mass was. So we didn't get to it. And I don't want to overwhelm you today rushing through it. But again, hopefully you can see that when we do the full course, and hopefully you will do the full course with me in September, let's say today we realized that was a problem, I would change the next lesson and we would do it again. And stuff we missed from this lesson, we would do again the next lesson. But because of summer school, this is our last lesson, we wouldn't be able to finish it. So yeah, we didn't get finished the workpack today, but it's because I don't know yous yet to see how fast we should be going. But hopefully when you do summer school, we'll figure each other out really quickly in the first 2 weeks. And then we'll always like adapt the lessons every time, right? It won't be us flying on. It'll be us saying, okay, we need to do this like 3 more lessons in this. And that's how it'll go. Same way school does, right? So you can see the rest of the stuff in your workpack, and you will do this with your teachers. I love this topic. But that's this type of stuff we'll be doing. So hopefully the 8 weeks of summer school has shown you what it will be like with me, but we'll just obviously go a lot slower. Gabriel, you're doing the STEM course, Happy Days. We'll go a lot slower. So when you have a problem with things, we can just slow down there and pause for a little bit. Just because I didn't teach these right. But this is my first time teaching, and it's all new topics. So summer school was me trying to give you a little insight into all the different topics that you'll do through the year. Monkey Pick a Pants as well. Happy Days. So just to let you know, and I hopefully you'll stay with us there for a second, just tell you about September course. So we know that it's roughly like £60 an hour for a tutor, right? I used to charge £50 an hour for a tutor, but my space, well, it's not fair, right? It's not fair that these people some kids can afford it, right? So, looking at it, if you had a tutor and you paid for one every week, you're looking at like 4,800 a year, right? So my SBS, what we're doing is we're trying to make that a lot more fair. And there's a big, massive discount for summer school. So in that link there on YouTube, you can see we're bringing it down to like 400 quid, and 400 quid for a full year of physics tuition. And we're teaching the full spec. So if you ever have problems in school, or you miss a day in school, or you're sick, or you just don't feel like you're listening to your teacher, or you can't get on, that's why it's been brought down to the 400. Yeah, so Sirianshi, it's different for year 12s than it is for GCSE. So just remember that to get that discount there. Savanic, your tutor's £80. Yeah, like tuition prices are going way up because teachers realize if everyone else is charging £80, they can too, right? But again, that's like loads of money to ask for one day. But if you look at this, if it's £400 for the year and we have 10 months of lessons, that's £40 for the month. In a month, we're having 8 lessons. So you divide that by 8, you're looking at £5 for a lesson, right? So it's £5 for a lesson. Oh, Garrick, I'm not really sure if that's a good way to put it there. Because I'm pretty sure most people who study physics are boys, and they probably see that thinking, nah, I'll take the PS5. So yeah, it works out at £5 a lesson rather than £80 a lesson, because we all know tutors for physics are mad expensive, right? Because a lot of schools don't have a really good physics teacher, which is quite sad. But there's a 14-day full refund guarantee, so there's don't have any risk with it. And there's loads of other subjects that you can have. So it's not just me doing physics, but hopefully you'll do physics with me. But there's also math with Dario, there's biology with Laura, there's chemistry with Joy. And some of you asked me last day about the timetable. So here's the timetable here. So you can see with me, so I think Monkey Pick a Pants there, and who was it? Gabriel, so they're going to be doing it with us. So we'll always have lessons from 5:40 to 6:40 on Wednesdays and Fridays. Yeah, and then you see all the other lessons there. So if you want to do all the other lessons, there's an ultimate pass where rather than you pay £5 a day for every single one of those lessons, there's even bigger discounts. So you can get all of your A-level subjects, and it basically works out at £2, £2 to £4 a lesson. Yeah, Gabriel, right? Yeah, and hopefully you guys will see that. Right? The whole point we did it was £70 and £80 an hour is ridiculous for a tutor, and like hopefully there'll be some day where it'll be a lot more fair. But £5 an hour is a massive drop from £80. So hopefully we're thinking, Tajuddin, you just woke up. Hopefully you're thinking that yes, we'll definitely do it with us next year because it'd be lovely to have you on the lesson. And if you did enjoy it, please do leave us a review on Trustpilot because everybody knows that, especially if you go on holiday or you go for dinner, everybody looks at Trustpilot to see if it's good or not. And a lot of people didn't do the summer school with us. And it'd be nice for them to see that your reviews to see, yes, it was good, what you liked about it, how it's different from school. Is it what you expected it to be like? So it'd be really nice if you could take like a minute and just like scan that there for us and do a shout out on Trustpilot about how you feel it goes. Savnik, you sound like a Raid Shadow Legend sponsor. What are you on about? But yeah, hopefully it's not the last time I'm chatting to you, right? But if it is last time, I wish you all the best with your physics next year. And hopefully it's not, right? Hopefully you'll see us. And even if you choose not to do the full course, we do Easter revision courses and cram courses coming up to your exams and stuff. But if you take anything from me before you go, year 12 matters, right? Your predicted grades that go to your universities are sent at the end of year 12, start year 13, and it's based on all the exams you did all for year 12. So you can't be going for year 12 and thinking, oh, my exams don't really matter. The grade doesn't matter. I'll get a D, 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 D. If you get a D all for year 12, your predicted grade will be a D, right? So you need to just make sure that you're trying to get those A's straight away. So it's A's straight away. Savanik, you're on my the September course too. Happy days. Angel, thank you for saying thank you. I hope you enjoyed it. Yeah, the my Savanik, thank you for saying the MySpace team, like the customer service is amazing. Like, what was the meme? Bye, Angel. Bye, Gabriel. Yeah, I mean it's our last one. So actually, the only things that so we do the TikTok. So on Tik, do we do the TikTok? That sounds weird. On TikTok, I do videos of explaining different parts of Year 12 physics and GCSE physics for yourself and exam questions. But the lessons, the ones where like me and you will be like talking all the time on chat, or like when people doesn't get an answer or they're telling me about their school day. So it's more like that's the September course. Amina, oh, I'm so happy to hear. Thank you for saying. Monkey Pig Pants, see you later. Yeah, Savanik, see you in the main course. Yeah, and then there'll also be like a chat we have. So like when you're not in the lessons and something goes on, you can like chat to each other and help each other out as well on the chat. Yeah, Savanik, see you in the main course. Yeah, Garrick, 100%. Yeah, so there is installments. Doesn't have paid all in one go. Yeah, 100%. Three installments for the year is how it gets allowed to. So if your course is like, if your course there we said was 400, it would be three installments of roughly 133. But again, it comes down to, I know if you look at the full course, full year, you might think it's a lot. But if you compare it to tutors, they're £80 an hour now, or £60 an hour, or I was charging £50 an hour. £5 an hour for a lesson is pretty solid. Like, sorry, Angie, hopefully in all of them, I should be anyway. So yeah, I probably go on Instagram more because I grew up with it. So I'm on my own Instagram anyway, like my personal one. So it's quite easy to flip onto the other Instagram page. But yeah, I do go on TikTok roughly every other day or every day. Yeah, so anyways, have any questions about the course or anything from me before you go? Or you've already left. I hope you have a beautiful, beautiful year of physics. And stay up for uni. Aerospace is all about like studying Big Bang theory. Is it a theory? What does it mean? It's about looking at the different layers of the sun and how it doesn't actually get colder the whole way out. It's looking at redshift, star formation. It's looking at orbiters of different planets, what we're discovering those planets. I loved it. And then aerospace engineering, if that's what you're talking about, is when you're talking about how to design spacecraft. So, for example, there's a lot of radiation in space. So, how you design spacecraft to withstand that or protect the people inside it. What about the heat when you're burning up as you're coming back down to Earth? If you want to become a pilot, there's quite different routes to go into becoming a pilot. So again, I know about this because I tried to be in the Air Force. But because I lived in America for too long, they wouldn't let me join until I lived here for a few more years. But you can't be a pilot in the Royal Air Force after 25. So I'm ready. I'm past that. But well, that was the rules when I looked at it, and that was like 8 years ago. So the rules might have changed since then. So these are the rules 8 years ago. But to be a pilot, there's quite different routes. So you can either go study aerospace engineering, like Monkey Picklepants said his brother was doing, and then go into pilot. Or instead of going to university, you can join pilot school. It's called flight school. I don't know what the prices are now, but 8 years ago when I looked into it, it was 50K for flight school, which seems like a lot. And at the time, I couldn't afford it. But if you think about university, it's 9K a year. And you have to do it for 3 years. That's eight, three nines or 27K, 30K. And then plus your cost of living on top of all that, you're basically approaching most people come out of debt of uni of like 40, 50K anyway. So if that's what you choose to do, you go into it. So I know my friend's brother, she did that. He did the flight school, and now he's a commercial pilot. So there's quite a few different ways to go into being a pilot. Or you can join the Air Force young age, and sometimes they'll pay for your education as well to be a pilot while you're studying. So they'll pay for your education because you're going to work for them. 37K for 4 years, like it's mad. It's so expensive. Luckily for me, I only had to pay 1 year of uni because I did my undergrad degree in America because I got a full ride. It was all paid for. But I had to do 1 year master's, and I was 18K in debt for 1 year master's. Like it's mad. It's madness. Astrophysics is not. Astrophysics is more like if you want it to work with studying stars. It's not really to do with being a pilot. But again, to be a pilot, like Eric said, you don't have to have a degree. It was more that I did a degree because I wasn't sure yet what I wanted to do. So I wasn't ready at 18 to say that I'm done and I'm 100% sure I want to be a pilot. I thought I wanted to be an astronaut, but I wasn't sure at 18 to make that choice. So that's why I went to America for uni. And then when I came back from America, I was sure for the choice, but because I lived in America for too long, I couldn't be a pilot. That's why I went into my master's. How much do you earn? You can, if you join the full course, I can tell you that. I'm not gonna. This is a. Or you can look up Neil. So Neil does math. Neil's done a few interviews with different papers, and he said his salary on those. You can't ask people their salary. But yeah, so like I'm gonna be fully employed with them with September for my space. Right now I'm a contractor, so because I'm still working for my other school, kinda. Yeah, Garrick, like 100%. Yeah, like it's annoying to have debt, but like yeah, you basically it's annoying when you get a salary and it comes out every now and again, but you barely notice it. You're right. How much does a pilot earn? Really significant difference in salary. It depends what you want to do. Like, I mean, significant differences. If you're a commercial pilot and you're flying like Dubai Airlines or wherever, I can't remember the airline's called, like you're talking loads of money. If you're flying Ryanair, a lot less. If you're in the Royal Air Force and you're flying helicopters, a lot less than if you're in the Royal Air Force and you're flying fighter pilot jets, right? It's quite a significant range of salaries. Right. Well, I'm gonna hit the road because I need to go to the bathroom as well. uh, Yeah, Siranshi, I saw your message. I messaged you back on TikTok about it. But have a lovely day, and I will see you guys hopefully, well, a few of you in the September course. Hopefully, I'll see a lot more of yous. It's been a pleasure.